Good morning, everyone. You've now learned a bunch of detection techniques, and we're going to continue applying those to study the demographics of planets. Our first speaker this morning is Professor Brendan Bowler, who is at the University of California, Santa Barbara. He will be telling us about the demographics of gas giant planets, and then we'll work our way down towards smaller planets. Enjoy.
Thanks. Thanks, Courtney, and thank you to the organizers for this invited talk. I have the pleasure to tell you about the history of demographics as we've come to learn them for the easiest planets to detect, the gas giants. And I'm going to use the analogy throughout the talk of a quilt. Demographics, as we've come to learn this week, is really a tapestry of many patches of quilt from different techniques, different methodologies, different biases. And the best we can do right now is really try to stitch them together to learn something about where planets form, how they form, and how they evolve in their orbits, and also, of course, thermally over time. So to make sure we're on the same page, I just want to highlight that, let's see, I will be focusing on, or I'll define the threshold for the purposes of this talk as a Saturn for no particular reason other than we have one in the solar system, and anything below that becomes progressively harder to detect. So giant planets, they're the most obvious planets, both in terms of detectability and their impact on planetary systems. So, of course, they dominate the mass budget of planetary systems. Their planets are negligible to first order for any star. But at least in the solar system, they represent the gas giants Saturn and Jupiter represent about 90% of the mass budget. They also, of course, represent most of the angular momentum budget. So the collapse of a cloud core preserves angular momentum, and much of it is imparted into the orbits and rotation of planets. Their dynamics are important for habitability, both in terms of their location. So, of course, they can disrupt and create a zone of dynamically unstable territory where lower mass planets cannot reside. This is a plot from a student of mine, Katie Painter, where she shows the normalized habitable zone for all of the HWO precursor target list stars. And so all the planets here are known giant planets, and the gray regions show the regions of dynamical instability. And this just is to show that demographics matter. If nature forms many giant planets at about 1 AU around sun-like stars, then that does not bode well for the search for life. So demographics of giant planets matter. They also, of course, may impact planetesimals and the bombardment of the inner solar system and inner planetary systems. And their eccentricities matter. Giant planets are dynamically hot in general. And so they carve out much of their planetary system landscape in a way that is inhospitable and dynamically unstable for any planets. But of course, they're also the easiest to detect, so we know quite a bit about them, spanning many decades of separation. So for transits, the transit depth scales as the radius of the planet squared. For radial velocities, the semi-amplitude scales as planet mass for a given inclination and orbital period and stellar host mass. When considering direct imaging, the bolometric luminosity or flux of a planet scales as m to approximately the 2.5 power. The star-planet contrast scales as the planet radius squared, both in reflected light and in the Rayleigh-Jeans tail, or Rayleigh-Jeans approximation in thermal emission. And the astrometric reflex motion of a planet or of a star scales as the mass of the planet. So these indices are all at the level of 1 or 2, and it just goes to show that size and mass matters. So demographics is really a quilt. It's stitched together from many different techniques, as you've learned about in the hands-on group sessions over this past week. And that means several things. So for the stars, it means we're sampling many different stellar kinematic properties, metallicities, locations within our galaxy. So for transits, these are typically identified from wide field surveys. And because of that, the host stars tend to be quite old, several gigayears in general. By design, at least for Kepler, they are roughly solar mass, and TESS is somewhat more unbiased to the present day mass function. And so it tends to focus on lower mass stars. So we see a lot of planets raining down from the sky around low mass stars from the TESS mission. And they tend to be moderately distant, a few hundred parsecs, let's say on average. Radial velocity surveys are much more targeted and focused, typically on bright field stars. Also by design, they tend to be old and predominantly sun-like. It's very hard to go to high stellar masses and high temperatures. And low mass stars present their own challenges. And they tend to be nearby because of this bias towards bright stars. Microlensing also, of course, is a wide field technique. It's statistical in many ways. The stars tend to be old and somewhat lower mass, not exclusively, but somewhat. And the distances are vast, so kiloparsecs on average. And finally, with direct imaging, and there are a couple flavors of this right now, of course, in the community, we're dealing with thermal emission. These are targeted surveys. Planets are brightest at young ages, so we tend to focus on younger stars, and we also like nearby stars so we can reach closer inner working angles. These have predominantly been sun-like and intermediate mass stars. There are some low mass programs as well. And they all tend to be nearby star-forming regions. So within about 150 parsecs, most of the youngest, largest clusters are between about 100 and 150. And there are nearby, somewhat older, young associations within 100 parsecs. So the host stars are different. You can already imagine the wealth of biases and evolutionary trends that might emerge just within those subset of stars. We're going to ignore all of that in this talk. And then we're also limited by what the techniques probe. So transits probe planet size, RVs probe the minimum mass. Microlensing typically probes star-planet mass ratios, and direct imaging probes planet luminosities. And so we need models to convert that into masses. So why does all this matter? We might be ignoring potentially important effects like age and evolution, host mass properties, multiplicity, which is much better known in some of these territories than others, host metallicities, and then also questions like birth environment. So when we're probing young stars with direct imaging, for instance, are we probing a subset of the stellar population that might be very different from field stars, which are typically produced in large OB associations with memberships at the level of 10 to the 4 stars. We tend to probe young clusters with direct imaging that have memberships that are low density and have memberships of, say, a few hundred members. There are many reviews at this point on demographics, and I just want to highlight one that I especially like. This is from Scott Gowdy. I won't go into detail here, but there's a lot of discussion about the methodologies that are typically used in the field and some of the cautionary tales to keep in mind. So when we think about demographics, it's good to consider rewinding the clock to the initial conditions. We now know with ALMA that protoplanetary disk properties, masses, radii, to levels of substructure are very diverse. This is a representative gallery, and there are many more by a factor of several at this point in both camps, in scattered light on the left and in dust emission from sub-millimeter observations on the right. Now we know that disk masses scale with stellar mass. There's a large dynamic range of disk masses for a given age. And the disk size distribution is also broad. So for a given host star mass, the disk mass scales with a range of disk masses span about 2 orders of magnitude. The dynamic range for a given age is also about 2 orders of magnitude and at least 1 order of magnitude for disk sizes. So we're sampling a large variety of properties. And of course, planetary systems inherit this diversity. One of the benefits of giant planets is that they, because of the readiness of their detectability, they can be studied across the entire scale of protoplanetary disk sizes and even beyond that. And so it's the most complete population that we have. If we consider a particularly large disk like HD 169142, which has a size of about 100 AU, of course, the transit method only probes a tiny inner region of that large disk. Radial velocities, all the hard work that many people in the room here have been carrying out for 30 years, only gets us to a few AU. And direct imaging covers a large swath of territory, but we're insensitive at this point to lower planet masses, typically lower than a few Jupiter masses. In the best cases, about half a Jupiter mass. JWST is helping with that. So for this talk, we're going to discuss this rectangle here, and Chaz introduced this concept on day 1 of probing the elephant with many different techniques. So we're going to try to take a picture here of this blurry elephant by synthesizing some of these methods. And it's also just worth noting that not only are we sampling the different methods and different host star properties, but of course we're incomplete, at least for high contrast imaging out to these separations. But let's see what we arrive at. And it's also worth considering, the exploration of demographics is not just an exploration of, say, new continents, as was done in the history of humanity across millennia. But it's also grounded in physics and the science and the questions that we want to have answered. For instance, formation, which operates on many different timescales and over many decades of separation. So core accretion operates on typical scales of an AU to maybe tens of AU. Disk instability for massive cold protoplanetary disks that have sufficiently large masses and mass ratios that they can collapse. Operates on somewhat wider scales, tens to hundreds of AU. Cloud fragmentation can also produce low mass companions at wide separations. The details of that process and how it's imparted on the demographics that we observe is not quite clear yet. And it's also possible that in natal clusters, dense clusters, low mass companions or perhaps even ejected planets can become bound and captured to some of the stars that we're focusing on in the solar neighborhood. So all of this spans 5 orders of magnitude in separation. And it's, of course, complicated by migration. So there are many pathways of inward migration at early ages through protoplanetary disks, and then over many decades of time scale beyond that, through planet scattering and secular interactions like high eccentricity migration and tidal capture. Planets can also migrate outwards, also through planet scattering and through resonant processes. And so all of this is really to convolve the imprint of the initial conditions with evolution. So it makes our task challenging. So I won't come to any grand conclusions or interpretations here, but let's just summarize what we know. And so here again, we're marginalizing essentially over many interesting parameters. So hot Jupiters, and I'll highlight some reviews here. I won't go into detail, but for each of these categories, I'll list them, and I encourage everybody to explore them. So the occurrence rates are small for this extreme population of giant planets close to their host stars. The typical rates are about at 1%. There have been some differences between radial velocity surveys and transit surveys at the level of a factor of a few, but they're all at the 0.5 to 1% level. And there's been speculation that maybe it involves the metallicity distribution of, say, Kepler stars, differing from that in the solar neighborhood, or perhaps unresolved stellar multiplicity. There's a nice quote in a review from Josh and Eric that we should never lose too much sleep over these 3 sigma discrepancies. And indeed, there's a nice study from Belesne and Kunimoto a few years ago that found that single stars from tests have occurrence rates of about 1% but binaries have an occurrence rate of about 0.5%. So it seems like that might help address that question. There's a few day pileup of hot Jupiters. So there's structure in the period distribution. Hot Jupiters peak at about 3 to 5 days. It's not quite clear, I think, what the origin of this is, but it probably relates to um, something about the inward migration mechanism or mechanisms of hot Jupiters. Perhaps the inner truncation radius of a protoplanetary disk, or the region where tides really start to impact. And interior to that, tidal decay operates more efficiently. There's a steep dependence of giant planet frequency with stellar metallicity. The occurrence rate rises by a factor of about 10 over only about half a dex in metallicity. So this could be an indication that, as you crank up the metallicity of a protoplanetary disk or the star, and therefore the protoplanetary disk, the rate of giant planets may increase, perhaps proportionately, and that might increase scattering. It's not the only idea, but it's one that is at least consistent with these observations. And there are, I would say, hints that there's an evolution of the occurrence rate over time. So when dissecting ages for most of these hot Jupiters in the field, there seems to be a trend that there are somewhat fewer at older ages compared to younger ages, whereas cold Jupiters seem to have a roughly constant occurrence rate over time. So this could be a sign of tidal decay. Okay, let's march out to warm Jupiters. I've never seen a consistent definition of warm Jupiters. Here, let's just call them maybe 10 days out to 1 AU or 365 days for a sun-like star. But I'll be loose with that, and we can also kind of include some studies that go out to 2 AU. So warm Jupiters in general are also fairly rare, and in many ways rarer than hot Jupiters. Hot Jupiters have an occurrence rate of about 1%. Warm Jupiters out to 1 AU have a comparable occurrence rate, but over a much larger range of separations. So at least per separation bin or logarithmic bin, the occurrence rate is comparable or perhaps even smaller. But there's a sharp rise at about 1 AU, and this has been seen in many surveys. So this is an important feature that we'll talk about in the cold Jupiter territory that seems to be intrinsic about the planet formation and migration process. So this could be an imprint, perhaps, of the water ice line. The occurrence rate is also steeply dependent on both stellar metallicity in an exponential way and stellar mass in an approximately linear way. This is work that's been known for a very long time, originating all the way back to Santos et al. 2004 and Deborah's work with Jeff Valenti in 2005. And many studies since then. Here I'm showing off this joint relationship between mass and metallicity from John Johnson in 2010. So this could be a signature of more efficient core formation. So as the metallicity of the disk and the mass of the disk is cranked up as you go to higher masses and higher metallicity stars, that seems to imbue more, or seems to make it more likely that perhaps cores form. There's a degeneracy in that interpretation, or there's some ambiguity in that interpretation, in that if most giant planets form beyond the water ice line, that's an if, but that seems to be the case, at least in the field, then it could also involve a more efficient migration to inner separations and shorter periods. There are also hints of an increasing occurrence rate over time. This has now been seen in a few programs at the sort of 1 or 2 sigma level, but there are efforts to combine these programs. These are results from a student of mine, Quan Tran, who's now graduated and a postdoc at Yale. He spent 40 nights with the Hobby Eberly Telescope's Habitable Zone Planet Finder trying to find planets around young stars in the solar neighborhood, with the goal being to compare that occurrence rate to the measured value in the field to search for signs of this evolution. The final results are quite broad, and so it's consistent with a constant occurrence rate, but there are certainly hints from the one discovery in his program that that occurrence rate might be increasing. And similar results have been seen for Antoine Grandjean and Anne-Marie Lagrange's work in Europe. There's, marching out to cold Jupiters, there's a peak in this giant planet distribution function. This is one of the most remarkable stories, I think, in my mind, that at least three independent long-term radial velocity programs have found more or less the same thing. This sharp rise in planet occurrence rate at 1 AU, and essentially a constant rate out to the longest baseline programs, really going out to about 30 years. And there's now a marked and significant turnover in this frequency of giant planets at about 8 or 10 AU in that territory. There are uncertainties with some of the properties, I think, of some of the planets, and the sample size starts to dwindle, but this turnover appears to be real. So I think we really are starting to map this cliff in where giant planets form and where they're now located at old ages. As we march outward to distant planets that are recoverable with high contrast imaging, the occurrence rate falls with distance for more massive planets. So typical high contrast imaging surveys bottom out, at least from the ground, at a few Jupiter masses. So we're really talking about the most massive members of the planet population, 5 to 13 or 20 Jupiter masses in that territory. But from the range of surveys and the increasing sensitivity and inner working angles that have been enabled with extreme adaptive optics instruments like GPI and SPHERE, these programs are showing that even at these wide separations, as we march outward, there's a declining occurrence rate, or equivalently inward, there's an increasing occurrence rate. So this 10 to 100 AU region seems to be more rich in super Jupiters compared to a few tens to a few hundreds of AU separations. So I think we're in direct imaging, we are reinforcing this cliff in the occurrence rate. This frequency also scales with stellar host mass. So as you crank up the mass of the star, there's now, I think, pretty solid statistical evidence that more massive stars harbor more massive distant giant planets. This is something that wasn't known for a long time, and it really takes dedicated surveys and efforts and a lot of effort to tease these apart. But more or less exclusively, the planet population that have been imaged reside around high mass stars. Not some of the famous ones, PDS 70 and a few others don't fall in that bin. But predominantly, the directly imaged planets occupy or orbit stars more massive than about 1.5 solar masses. And finally, there's a really interesting population of very distant planets. I believe the record setter is about 8,000 AU, and it's not quite clear how this population relates or connects to the inner population, where, of course, most of the protoplanetary disk mass and surface density is. So perhaps these are ejected planets, or perhaps they are simply the tail end of binary star formation from a traditional cloud fragmentation process. But regardless, we can measure how common they are. They seem to have frequencies of about 1% on average. There are a few programs, and you don't need adaptive optics for many of these programs. You can just carry out deep imaging from the ground, or even with facilities like WISE. So they're there. They're not common, and they seem to also reinforce this tail end of the distribution function. Okay, so if we just simply and naively add all of this together, we get something like 20, 25%, maybe up to 30% for the frequency of giant planets. And this seems to be in good agreement with results from Rachel Fernandez from her 2019 paper. They found, with modest uncertainties, an occurrence rate of about 30%, and from the CLS program, about 23%. And these are stitched together. These bins of planet mass are somewhat different, but altogether it seems to be a few tens of percent for sun-like stars. Okay, so what does all this mean? What is this telling us? The water ice line around the sun and sun-like stars is a few AU. And so we may be witnessing the combination here of increased disk surface densities at smaller separations, perhaps combined with this increased facilitation of giant planet formation beyond the water ice line. So perhaps this is a simple explanation, and maybe not the final one, but a simple explanation that can account for this increase in giant planet frequency. And then at distant separations, the typical protoplanetary disk size is a few tens to perhaps a few hundred AU. So that seems to be in line with the tail of the demographics that we're seeing. I'm just going to race through in a few minutes here, or in about a minute, what we know about orbital eccentricity. So hot Jupiters tend to be circularized. As we march out to warm Jupiters, they take on a broad range of eccentricities. In fact, most warm Jupiters, about 75% or so, are eccentric and not consistent with circular orbits. So they're dynamically hot. There's new work that Sarah Blunt is leading, looking at eccentricities for cold Jupiters, and they're finding that there perhaps is a planet mass dependence on the eccentricity distribution of cold Jupiters. But regardless, they are also dynamically hot. And yet for the super Jupiters at wide separations, they appear to be not only distinct from the brown dwarf eccentricity distribution function, but they tend to have predominantly circular orbits. Now, we're not probing entirely the same phase space, but we're starting to learn clues about eccentricities over all of these decades in separation. And I think the takeaway point for eccentricities is that planets are dynamically hot, and that tells us something about how they interact or interacted in the past. I'm going to skip through these questions just for the sake of time, but there's a lot to be learned about planet multiplicity, demographics over time, demographics of Saturns, and questions like birth environment that I think we still don't know much about. But I'm looking forward to the future. Gaia DR4 in particular is going to tell us about cold Jupiters and their prevalence and how they evolve over time. And so this is going to be a new patch that we can add to the quilt. And of course, Roman, we heard about earlier this week, will teach us about, at least statistically, about planets all the way down to the massive Ganymede. So I'll put up the takeaway points and happy to take questions. Thanks.
Thank you, Brendan. Okay. Are there any questions online or in the room? I have a couple. All right, so I'm going to take chair's prerogative and ask one while you all think of questions. And I want to encourage early career people in particular to come forward and ask questions. So my question is that you've shown us some really exciting results, but you've also emphasized that our knowledge is incomplete. If you could wave a magic wand and get a data set that had the properties that you're missing, what would you put in that magical data set?
I like that question. It's hard. It's hard. There's no single technique that for individual stars can take us all the way from close in to far out. I will just highlight, just to ground it in near-term realism, Gaia DR4 is going to be super exciting. So again, we've discussed this week, but it's immune to many of the challenges that we face with other methods. And planets can't hide from astrometry. You either have a wobble this way if it's edge on, or you have a face on orbit and it's wobbling like this. So as long as you reach sufficient precision, which Gaia does, the planets can't hide. So I'm especially excited about questions like, when do giant planets interact? When do they become dynamically unstable? Is that at the scale of 10 million years or 100 mega years or a giga year or a few giga years? When does that process happen? And also questions like, I didn't get into it here, but stellar obliquity. So how does stellar obliquity evolve over time? And I think we can begin to answer these kinds of things with Gaia in that sweet spot of giant planet formation.
Excellent, thanks. Any other questions? All right, I see someone getting up. I'm also going to acknowledge there's a question online about massive rocky planets, which I think is better suited to some of the future upcoming talks because Brendan's focusing on gas giants. But go ahead. Probably have time for only one of you, sadly. Be sure to put your questions on Slack if you don't get a chance to ask them now.
Okay. Hi. So thanks for that great overview. I was just wondering if you could say a few words about maybe the challenges and promises of using like population synthesis type models to describe, especially this hot population of these giants, especially their migration histories for warm Jupiters and hot Jupiters, and if you've thought about that at all.
Yeah, I think everyone's probably thought about that a little bit. Yeah, great question, Brendan. Um, I, I think they're important. You know, many of us kind of divide ourselves into camps of observers or modelers or theorists, and we have to unite and we have to talk to move the field forward and really, frankly, just interpret these results. You know, it's one thing to spend careers just making measurements, but the measurements are nothing without an interpretation. And I think these synthesis models are the exact kinds of things that we need. I'm going to take your question and move it to cold Jupiters because I think that we have an opportunity, the field does, to make the kinds of statements or predictions that folks before Kepler were making. So there are many famous papers that some of you might not be aware of where modelers did exactly that thing. I'm thinking of Ida and Lin and many papers of that flavor. There were predictions. They did not all pan out, and that's okay, but they move the field forward and they make testable hypotheses. We need that for giant planets. I want to know what the models say and how to interpret when we make these measurements of eccentricities over time or demographics. Are there predictions of structure in the radial distribution function? Should we expect peaks at snow lines, at water and CO, et cetera? And I haven't seen a lot of that. So I encourage the modelers and the theorists to really think carefully and go out on a limb and make those predictions now before DR4 happens.
Great. Thank you again. Let's thank Brendan Bowler again.